For nearly 50 years, Voyager 1 has traveled farther from Earth than any other human-made object. As it continues its journey through interstellar space, the spacecraft has become the center of countless online theories. Some claim it has discovered hidden structures beyond the solar system or detected mysterious objects lurking in deep space. These stories are captivating, but they are not supported by the mission's scientific data. Voyager 1 was never designed to photograph distant objects beyond the solar system. It carries no powerful telescope capable of scanning vast regions of space. Instead, its instruments perform something equally valuable. They measure the environment immediately surrounding the spacecraft, recording magnetic fields, charged particles, plasma and cosmic radiation as it travels through space. And what Voyager has actually discovered is extraordinary. Not because it found alien megastructures but because it revealed that the space between stars is far more active than scientists once imagined. The story began in 1977. NASA launched two nearly identical spacecraft, Voyager 1 and Voyager 2, during a rare alignment of the outer planets. This fortunate arrangement allowed each spacecraft to use the gravity of giant planets like stepping stones, dramatically increasing their speed while conserving fuel. Voyager 1 reached Jupiter first. The images it returned transformed planetary science forever. Scientists witnessed enormous storms raging across Jupiter's atmosphere, powerful radiation belts surrounding the planet and a complex family of moons unlike anything previously observed. One discovery proved especially remarkable. The moon Io was found to contain active volcanoes. Before Voyager, many researchers believed small worlds so far from the Sun should be cold and geologically inactive. Instead, Io was erupting with tremendous energy. Scientists realized that Jupiter's immense gravity continually stretches and compresses the Moon, generating internal heat capable of driving continuous volcanic activity. This process, known as tidal heating, completely changed how planetary scientists think about geological evolution. Voyager then continued toward Saturn. There, another surprise awaited. From Earth, Saturn's rings appeared smooth and continuous. Up close, Voyager revealed an astonishing level of complexity. Thousands of narrow ringlets, spiral waves, gaps and delicate gravitational patterns filled the system. Tiny moons interacted with the rings, sculpting intricate structures through their gravitational influence. Saturn was no longer simply a planet surrounded by rings. It became an entire dynamic system governed by constant motion. After completing these historic planetary encounters, Voyager entered a completely new chapter. Its planetary mission ended. Its interstellar mission began. For decades, the spacecraft continued traveling toward the outer boundary of the Sun's influence. Then, in 2012, history was made. Voyager 1 crossed the heliopause, the outer boundary where the solar wind gives way to the interstellar medium. Contrary to many artistic illustrations, this boundary is not a giant wall or visible barrier. Instead, scientists identified it by observing gradual changes in particle populations, plasma density and magnetic conditions surrounding the spacecraft. Crossing the heliopause meant something extraordinary. For the first time in history, humanity possessed a spacecraft directly sampling the environment between the stars. The region beyond our solar system was no longer purely theoretical. It had become measurable. Entering interstellar space did not mean Voyager traveled into complete emptiness. Quite the opposite. The spacecraft revealed that the space between stars contains an incredibly thin mixture of ionized gas, magnetic fields, energetic particles and cosmic radiation. Although these materials are spread across enormous distances, together they form the interstellar medium, a vast environment constantly shaped by exploding stars, stellar winds and galactic magnetic fields. One of Voyager's most important discoveries came from its plasma wave instrument. By measuring tiny oscillations traveling through ionized gas, scientists were able to calculate the density of interstellar plasma surrounding the spacecraft. These waves are sometimes described as the hum of interstellar space. While the phrase sounds mysterious, it refers to a completely natural physical process. They are not radio transmissions or artificial signals. They are simply vibrations moving through charged particles in space. Even so, these measurements were historic. They provided humanity's first direct observations of conditions beyond the protective influence of the Sun. As Voyager continues its journey, it has shown that interstellar space is anything but uniform. Some regions contain slightly higher concentrations of plasma. Others display subtle changes in magnetic field direction or particle density. These variations likely reflect enormous structures created over millions of years by ancient supernova explosions, stellar winds, and the magnetic architecture of our galaxy. Rather than moving through an empty void, Voyager is traveling through a changing cosmic environment shaped by the evolution of countless stars. Yet there are important limits to what the spacecraft can do. Voyager cannot map distant objects or search for enormous hidden structures. Its instruments only measure local conditions where the spacecraft happens to be at that moment. Over time, these individual measurements gradually build humanity's first direct profile of interstellar space. Keeping Voyager alive has become an engineering achievement almost as impressive as its discoveries. The spacecraft is powered by a radioisotope thermoelectric generator that slowly produces less electricity each year as its fuel naturally decays. To extend the mission, engineers have carefully switched off non-essential systems while preserving the remaining scientific instruments. Communication presents another enormous challenge. Because Voyager is now so distant, a radio signal requires more than 22 hours to travel one way between Earth and the spacecraft. A command sent today cannot be confirmed until nearly 2 days later, and complete testing often takes several more days. Every adjustment demands extraordinary patience and careful planning. Despite its age, Voyager continues sending valuable information back to Earth. Its observations help scientists better understand how our solar system interacts with the wider galaxy and how cosmic radiation behaves beyond the heliosphere. Beyond science, however, Voyager carries something even more meaningful. Attached to its side is the famous Golden Record, a collection of music, greetings, natural sounds, and images representing life on Earth. It was never intended as an active message to extraterrestrial civilizations. Instead, it serves as a symbolic time capsule, preserving a snapshot of humanity for an unimaginably distant future. Eventually, Voyager's remaining instruments will fall silent. Its power source will no longer be able to sustain communication with Earth. But the spacecraft itself will continue traveling through the Milky Way for millions of years. Its greatest legacy is not internet speculation or sensational theories. It is the remarkable fact that a machine built in the 1970s became humanity's first true explorer of interstellar space, proving that the unknown beyond our solar system is not empty, but rich with scientific discovery.